Hello. Today we are going to be on day 2 of transformations. So our goal today is to be able to write a transformation of a parent function. So again, our lesson the other day had us talking about parent functions and how it shifts our graph. Now we're going to talk about actually creating an equation given an already shifted graph. All right, so give the name of the parent function, describe the transformation represented. So we have g of x equals 2 times the quantity x minus 3 squared plus 1. Parent function is going to be x squared. And again, our parent function is the function without any shifts or transformations. And the transformation here, if you need to look back at your notes from our last video lesson that explains what our A, B, C, and D values do, you can go ahead and do that. But in this case, since we have a C value of 3 and a D value of 1, it's going to shift right 3 up 1. And since our A value is 2, we have a vertical stretch by a factor of 2. And the reason why, again, that's an A value is because it's not part of the input. It's not actually being squared. And that's why this is a C value, because it is part of the input. It is being squared, and why the 1 is our D value, because again, not part of the input. It's not being squared. All right, B. Our parent function is the rational function, 1 over x. And in this case, our rational function is going to be shifted, since I have a C value of 4 and a D value of 2, to the right 4 up 2. Again, I know that's my C value because it's part of my input in the denominator. And then plus 2, again, I know that's my D value because it's not part of the input. Example 3, remember you have to factor the negative 2 out when you have a B value that's not factored out. In order to correctly identify your C value. So we factor that negative 2 out. So really this is the square root of negative 2 times the quantity x minus 2. So we have a B value of negative 2 and a C value of positive 2 on our parent function square root of x. So this is going to be a horizontal compression by a factor of 1/2, because remember, the B values have a reciprocal relationship with the factor. It's 1 over B times x. So a horizontal compression by a factor of 1/2, and shifted right 2, and then reflect over the y-axis because the negative of the negative 2 reflects over the y-axis. And we have a negative B value. All right, next example, negative 3 times the absolute value of x plus 8, parent function, absolute value of x. And our transformation here, we have an A value of negative 3 and a D value of 8. So we have a shift of 8 and a vertical stretch by a factor of 3, as well as a reflection over the x-axis, because the negative A value gives us a reflection over the x-axis. And our last example, f of x equals negative x minus 7 cubed. Remember, if our B value is negative, you have to, or is anything other than 1, you have to factor it out. Again, I know it's a B value because it's actually being cubed, so it's part of the input. So in this case, we have a B value of negative 1, C value of negative 7, and a D value of negative 4 on our parent function x cubed. So this is going to be shifted left 7, down 4, not floor, and reflected over the y-axis. Because again, a negative B value reflects over the y-axis. All right, example 2. Given the parent function and a description of the transformation, write the equation of the transformed function. So absolute value is our parent function, vertical shift up 5, so our D value is 5, horizontal shift right 3, so our C value is 3. So we end up getting f of x equals the absolute value of x minus 3 plus 5, because again, it's always f of x minus c, so the opposite of c. And remember, B and C always part of the input, A and D not. So since absolute value of x, my c value is within the absolute values, and my d value is not. All right, radical, so square root, with a vertical compression by 2/5 and a horizontal shift of 1. So that means our a value is 2/5. Horizontal shift of left 1 means -1. So when we have it in our equation, we're going to see it as a +1. So g of x equals 2/5 times the square root of x plus 1. And just in case you don't have your equation out with you, or your notes from last lesson out with you, I am going to really quick write again from our notes from our last lesson, the form. So we have a times f of b times x minus c plus d. So again, if we have a vertical shift d and a horizontal shift c, that's why we have -3 in absolute values and then the +5 outside. All right, and same thing for our next one, since the vertical compression, I know that that's an a value, and a horizontal shift, left 1 horizontal, right, we know is our c value. All right, so c, cubic, reflected over the y-axis and vertical shift down 2. So our parent function is x cubed, reflected over the y-axis means that we'll have a -b, and a vertical shift down 2, so that's our d value of -2. So we end up getting h of x equals -x cubed minus 2. Rational, vertical stretch by 8. So vertical stretch, that's A, and a horizontal shift left 4, so that's our C value. So we end up getting, come on, there we go. K of x equals 8 over x plus 4. And then our last example, the quadratic reflected over the x-axis and a vertical shift up 6. So reflected over the x-axis, again, means a -a value. Vertical shift up 6 is a d value, so +6 for our d. So we end up getting j of x equals negative and then x squared plus 6. All right. Example 3. So the graphs show parent function and 2 other translations of the same function, g of x and h of x. So use the graphs to derive their equations and write the function in a form that indicates the transformations of the parent function. All right, so our parent function is f of x. This is f of x equals x squared. So looking at g of x, it looks like our vertex, and the key to these is to first identify that critical value. So in this case, our critical values are vertex. So our vertex was shifted to the right 1, 2, 3, down 2, which means that we have a C value of 3 and a D value of -2. And then it looks like our vertical stretch is 2, because when our parent function, normally you go right 1 up 1, right 1 up 3, right 1 up 5, but instead we went right 1 up 2, right 1 up 6, and then I bet if we kept going, it'd be right 1 up 10, but we ran out of graph. So our vertical change is being multiplied by a scale factor of 2, which means our A value is 2. So we end up getting 2 times the quantity x minus 3 squared minus 2, once we, again, substitute that into our transformation equation. And then h of x. So our vertex was shifted to the left. Let me change my color. To the left 6 and up 2. So our C value, -6, our D value, 2. And then it was reflected over the x-axis. So that means our A value is negative. And it looks like there's no change because we're going right 1, down 1, right 1, down 3, right 1, down 5. So no change in our actual vertical change, just the direction. So that means that our A value is -1. So we end up getting -1 times the quantity x plus 6 squared and then plus 2. All right, for our next example, our parent function is f of x equals 3 to the x. So the main thing here is going to be to identify how when we have exponential or logarithm functions, is to see how the axes changed. So in this case, it looks like, we'll start with g of x. Our axes shifted here. So our horizontal asymptote is now here at -5. So that means my d value is -5. And it looks also like we have a reflection over the y-axis. So that means our b value is going to be negative. And we also have a horizontal shift of the right 2, because we see how the point that was on the y-axis is now shifted to the right 2 here. So we put, so that means our c value is 2. So we put that all together, and let's see if there's actually a multiplier for our a or for our b. And looking at our point here, we went right 1 up 2. Here we're going left 1 up 2 because that reflection. So there's no change in our vertical or horizontal stretch or compression. So just a negative b value. So we put that all together and we end up getting not that. That is actually our equation for h of x. I wonder if I switched them. Let's see. So, yep, very good. Okay. So our equation for, let me fix that, g of x is 3 to the power of, now I have the negative distributed in, but if you wrote this as 3 to the power of -1 times x minus, the quantity x minus 2, and then -5 to keep it more like the standard form, that's totally fine. You can also get fairly fancy with this and apply the negative to the base and write it as 1/3 to the power of x minus 2 and then -5. But this actually then changes the parent function. So I wouldn't do this. I would leave it as either that option or that option with the b value factored out or distributed in. All right. So g of x, why is g of x what g of x is? So looking at the graph, again, it's key to see where the axes shifted to. So it looks like our axes shifted here. We have our horizontal asymptote is now at -3, so I have a d value of -3. And our y-axis looks like it was shifted to the left 1, 2, 3, 4. So a c value of -4. And we have a reflection over the x-axis. So that means our a value is negative. And looking to see if there's any sort of stretch or shrink. Again, looking at the change of our parent function, right 1 up 2. Here we have right 1 down 2 because of reflection. So all of that's good. So it's just an a value of -1, no stretch or compression. So that's how we end up getting that equation. All right, example number 5. Parent function f of x equals log base 2 of x. So we have our parent function here. So again, the key thing to do is see where our axes shift to. So for g of x, it appears that our axes shifted here. So it looks like there is no vertical shift, but there is a horizontal shift, left one. And it also looks like there is a vertical change. Instead of going right one, up one, right two, up one, right 1, 2, 3, 4, up one, it looks like we went right one, up two, and then, right two, up two, and then right 1, 2, 3, 4, up two. So our vertical stretch of 2. So that means that our A value, is 2. So our equation is g of x is 2 times log base 2 of x, the quantity x, plus 2. Oops, correct. Sorry, I messed up. This point shifted left 2. The axis shifted left 2, not left 1. Sorry, I counted wrong earlier. Now, if you're all looking at this, like, how did I know that that was a vertical stretch and not a horizontal stretch? It actually could have been a horizontal stretch of 2 as well. So an acceptable alternative answer would have been g of x equals 1/2, or log base 2 of 1/2 times x plus 2. So really, in this case, for a logarithm, you could have looked at it either way. All right, and then finally, h of x. So let's see where our axes shifted. So it looks like our axes shifted, our vertical asymptotes right here at -4, and then our critical value is right there at 6. So it looks like our axes shifted left 4, up 6. So that means that we have a C value of -4, a D value of 6, and there's also a reflection over the y-axis. So that means that we have a B value of negative, and then let's see if there's any sort of change in our rate. It does not appear so. We have right 1, up 1, right 2, up 1. Here we're going left 1, up 1, left 2, up 1. So that seems to be consistent, just the opposite direction due to the reflection, so -1. So we put that all together and we get h of x is log base 2 of -x minus 4 plus 6. And again, if you want to not distribute that negative in and write it as log base 2 of -1 times x plus 4 to keep it more standard, that is a-okay. All right, in our next example, parent function is f of x equals x cubed. So to find the equation for g of x, it looks like, and again, we want to take a look at our critical value. So for x cubed, that critical value is going to be that 0.00. So in this case, it looks like that 0.00 did not shift. So there's no C value or D value, but there is definitely a change here. So normally we're going right 1, up 1, right 1, up 7. But in this case, we're going right 1, 2, 3, 4, up 1, right 1, 2, 1, 2, 3, 4, up 7. So that means that there was actually a horizontal stretch of 4. So when we put that all together, we end up getting 1/4 x to the 3rd power. And again, 1/4 because it's always, for our input for these two values, B and C, the inverse. So for B, it's always the reciprocal of B. For C, it's 0. So I guess you don't see it there. So if it helps, you can write 1/4 here, because that's actually the value that goes there, and reciprocate here. Either way, whatever makes most sense to you. Oops, forgot about h of x. All right, and h of x, we have our critical value appears to have shifted left 4 and up 3. And instead of going right 1, up 1, it looks like we went left 1, up 1. So that looks like we have a reflection over the y-axis. So that means that our b value is negative. But it also appears that there's no other stretch or shrink, so -1. Now, if you're looking at this, like, how did I know that that was a reflection over the y-axis? Because it could also potentially have been a reflection over the x-axis. You are absolutely right. Because this is an odd function, odd parent function, it actually doesn't matter if you do a reflection over the x-axis or the reflection over the y-axis. So there are two potential correct equations. We can either have a negative b value like I have there, so negative x minus 4 cubed plus 3. Again, I have the b value distributed into the c value, but you don't need to. Or if you looked at this as a reflection over the x-axis, so again, instead of a negative b value, a negative a value, another potentially a correct equation would be -1 times the quantity x plus 4 cubed plus 3. All right, given the graphs, write the equation of the three functions f of x, g of x, and h of x. So in this case, we're not given the parent function, we just have to identify the parent function based on the graph and then the correct equation. So here we have, let's see, f of x. We'll start with f of x. So f of x looks like it is a quadratic. And identifying our critical value looks like which is our vertex for a quadratic. It was shifted to the right 6, so our c value is 6, and it was shifted up 5, so our d value is 5. Also, there's a reflection over the x-axis, so that means that our a value is negative. And it also looks like there's a stretch. So our parent function for x cubed, again, or sorry, x cubed, x squared, goes right 1, up 1, right 1, up 3, right 1, up 5. So this one's going right 1, down 3, right 1, down 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means that our vertical change is being multiplied by 3. So we have a vertical stretch by a scale factor of 3. So we put that all together and we get f of x equals -3 times the quantity x minus 6 squared plus 5. Now looking at g of x, which appears to be the square root function. So again, for a square root function, our critical value is going to be the start of the square root function. So parent function for square root of x, again, is 0, 0, 1, 1, 4, 2, like that. So here it looks like our c value is -6 because our initial point was shifted left 6, down 4. So our d value is -4. And we have let's see if there's any change in vertical stretch or vertical strength. So our parent function again goes right 1, up 1, right 3, up 1. So this goes right 1, up 1, right 1, 2, 3, up 1. So that did not change. So there's no change in our vertical stretch or vertical shrink or horizontal stretch or horizontal shrink. So no reflections. So in this case, our a and d value are just 1. A and b value, sorry, not d. So we put that all together and we get the equation g of x equals the square root of x plus 6 minus 4. And h of x, last one, parent function's x cubed. So again, x cubed, need to identify our critical value. So our critical value is going to be the middle of that snake squiggle. So normally it goes right here, like that. So our critical value was shifted left 5 and up 3. And normally this is, again, like that. So here we have either a negative a value or a negative b value, depending on if you see this as a reflection over the x-axis or a reflection over the y-axis. But either way, it doesn't appear, there doesn't appear to be any sort of vertical stretch, vertical shrink, horizontal stretch, horizontal shrink, because we still have that right one, down one, left one, up one relationship. So we have, again, two potential correct equations based on if you looked at this as a reflection over the x or y-axis. So reflection over the x-axis, we have that first equation, negative times the quantity x plus 5 cubed plus 3. Reflection over the y-axis, we have that second equation. And again, if you did not factor or distribute that negative in, that's okay. So that answer is just as good. All right, last example. H of x, linear equation. Just write the equation of the line. Y-intercept 8, slope down to right 1, down to right 1, so slope negative 2. So we have the equation, whoops, that was, I'm going back reverse order this time. So we end up getting the equation negative 2x plus 8. G of x. G of x looks like it is a exponential equation that's been reflected over the x-axis because we have a horizontal asymptote. And looking at the values, let's see what our change is. It looks like we have right 1, up 1, right 1, up 2, right 1, up 1, 2, 3, 4. So that looks like we have a base 2, or 2 to the x power. So shifting here, we have our normal shift, our asymptote, let me change the color. Our asymptote got shifted to 5, so our d value is 5. And it looks like our critical value got shifted to the left 1, 2, 3, 4. So we put that all together and we end up getting negative 2 to the x plus 4 plus 5. Again, because the reflection over the x-axis, the shift to the left 4, that's where the x plus 4 comes from, and then the shift up 5. And last example, f of x. F of x appears to have a vertical asymptote, so it's going to be a logarithm. So again, kind of looking at the base and the shift. So our critical value got shifted here. So our vertical asymptote is now at negative 6, and it does not, I'm sorry, so that's a C value, not a D value. And there doesn't appear to be any sort of vertical shift, so no D value. And now we need to look at our change. So here we have right 2, up 1, right 1, 2, 3, 4. 2, 3, 4, 5, 6, up 1. And then continue on. So it appears here that our base, that the base is 3, but just to be sure, let's graph the parent function really quickly. So we have logarithms. So log, if it's log base 3 of x, let's see. Log base 3 of 1 is 0. Log base 3 of 3 is 1, and log base 3 of 9 is 2. So that means that we would have 1, 0, 3, 1, and then 9, 2. So that changes right 2, up 1, right 1, 2, 3, 4, 5, 6, up 1. There we go. So it is log base 3. If you are not sure, because I'm going to be 100% honest with you. Exponential and logarithm parent functions are hard because every single one is different. So you cannot know base 2 and expect to then use that for a base 3 or base 5 or what have you. Each base is its own different parent function. So you have to be able to translate what we learned 2 chapters ago with logarithms to then figure out what this base is. So once you have your hunch of what base you think it is, graph the parent function, double check, is that actually the base, and go from there. So we end up getting f of x equals log base 3 of x plus 6, because again, only shift here was that there was a horizontal shift, left 6. All right, so I hope that you found this video educational. I have office hours again today at 4, so 4:30, or no, Friday at 10:30. So I will see you all then if you choose to come. If not, stay safe, stay sane, and please, please, please stay distant. Bye.